This is gases video number 1. By the end of this video, you'll be able to list and describe the 5 assumptions of the kinetic molecular theory of gases. As always, you will need the video worksheet that goes along with this and a pencil, because this will be due the next day you have class. Kinetic molecular theory. Kinetic has to do with motion. So this is the assumption that particles are always in motion, and therefore how they move will be able to describe the properties of the solids, liquids, and gases in terms of the energy of those particles and the forces between them. For the 5 assumptions of the kinetic molecular theory of gases, or sometimes called KMT, the first one is that the gas particles are in large numbers of tiny particles, and that they're going to be pretty far apart from each other in terms of their size. So here we see the particles of a gas, and it fills up the container. The particles are relatively small with big amounts of area from one particle to the next in comparison to their size, versus the liquids where there might be some distance between them, but it is smaller in comparison to their size, or the solids where the distance between them is so small is pretty much negligible. Next, the gas particles are going to be in constant, rapid, random motion, meaning that each particle is moving around its container, and when it hits the size of the container, it's going to bounce off and keep on going. Likewise, if it hits another particle, it's going to bounce off and keep on going. Gas particles are also considered to exist no attractive or repulsive forces on each other. This is pretty easy to see with something like carbon monoxide. Carbon monoxide is a non-polar molecule, and as a result, it doesn't have a positive or negative region. Because it doesn't have a positive or negative region, one carbon monoxide and the next carbon monoxide molecule don't attract or repel each other. This is different from water molecules, where you do have a positive and a negative side. It is a polar molecule, and water will attract another water molecule as long as the negative to positive regions line up. Water, therefore, is a liquid at room temperature. A lot of your gases are going to be non-polar. Number 4, the collisions between particles with each other and particles with the container walls are going to be elastic. Now, elastic in your clothing means it's going to snap back to its original shape. In this case, it means after it bounces back, the energy is going to be a constant, that you're not going to gain or lose any energy when a collision occurs. Now, we know in the real world, when a collision occurs, things slow down. But in this case, it's going to hit the size of the container, and however much energy it had right before the hit is how much it has after the hit. So the speed before the hit equals the speed after the hit. The last one has to do with the average kinetic energy of gas particles. The average kinetic energy is going to be directly proportional to the Kelvin temperature, which means if the temperature goes up, the kinetic energy is also going to go up. And because kinetic has to do with motion, it means that the speed of the particles will also increase. They're all going to be directly proportional. One goes up, the rest goes up. What does this look like in motion? Here we see our particles, the gas particles. They're pretty far apart from each other in comparison to their size. As they hit the size of the container, they're going to bounce off with the same energy they had before. But as the temperature goes up, they're moving much faster. The average kinetic energy means that some will have a little bit less energy, some will have more. But the peak is the temperature. As the temperature goes up, the speed also increases. The last thing you want to know is about the mass of the particles. Particles with a greater molar mass, such as these red ones, have a large molar mass found in the periodic table, move slow. The small ones with a smaller molar mass move faster, and then as the temperature goes up, they both increase their speed, but still, the larger molar mass particles will move slower than the others.